In this video, we're going to use the observation of the period for Charon orbit around Pluto and distance from Pluto in order to calculate the mass of Pluto, and then we'll calculate the density of Pluto. And this is not as simple as some other videos that I've posted where we can equate the gravitational force and the centripetal force. In this situation, the two objects' masses are comparable, and we'll have to use a slightly different approach. So I'm calling this not an elementary level problem. So this moon Charon was discovered in 1978, and the orbital period is 6.39 days. Point of trivia, Pluto also rotates once every 6.39 days, so it's sort of a double tidal lock. Our distance, the measured distance from Charon to Pluto, is 19,700 kilometers. And the two objects orbit a common point that definitely is not at the center of Pluto. Not going to calculate that point, but we're going to take advantage of the fact that the moon's orbit is 7.3 times the size of Pluto's orbit. That will give us information about the mass ratio for the two bodies. We want to do this mass calculation and compare it to the Earth's moon, and then we'll use the observed radius for Pluto to calculate the density of Pluto. Well, we might attempt to make a little sketch of this. This is not to scale, but gives you a little idea of what's happening here. Pluto and the moon Charon in orbit around a common point. And question mark, can we say that the centripetal force is equal to the gravitational force? And the answer is no. This method only works when one mass is much bigger than the other mass. We need something like the Earth going around the sun. That would work, or our moon going around the Earth also would be acceptable. But these two objects, their masses are too close to make use of this concept. Instead, we have to use the slightly revised version of Kepler's third law, that the period squared is equal to 4 pi squared a cubed divided by universal constant of gravitation, g. And then I have to add the two masses together. There's a sum of masses in the denominator here. So we use this revised Kepler's third law to come up with our answer. And we have the numbers. And my first step is just to solve algebraically for the sum of the masses. Notice this is not just the mass of Pluto. There's going to be another step later to find the mass of Pluto, but we're finding the combined mass here. So we have 4 pi squared. For A, we're going to put in our knowledge of how far Charon is away from Pluto, center to center, 1.97 times 10 to the 7th meters. That has to be cubed. And then underneath this, I've converted 6.39 days into the time in seconds. Let's slide this over just a little bit. 5.521 times 10 to the 5th seconds matches the 6.39 day value. So that goes in here, and that gets squared, p squared, period squared, and then our constant of gravitation. You should pause now and do this calculation, and hopefully you're obtaining on your calculator 1.48367 times 10 to the 22nd kilograms. But that's the combined mass. How do I find just the mass of Pluto? Well, we make use of the fact that the moon Charon has an orbit that's 7.3 times larger than the motion of Pluto. That means that their masses have a ratio of 7.3, with Pluto being the more massive object. It moves less, so it's the more massive object, and it's 7.3 times the mass of Charon. So I create the following setup here. These two masses are this particular number. I'm making a substitution here, getting rid of the mass of Charon and replacing it with mass of the Pluto divided by 7.3. So we're making a substitution for the mass of Charon. here, instead of just writing MP, to make it more visible perhaps on what I'm doing with the numbers, I'm doing 1 times MP, 1 times the mass of Pluto. So hopefully you'll follow how the numbers get added together. On the next line down, I've divided 1 by 7.3. That produces 0.137. I've factored off MP from both terms. So here I have 1 plus 0.137 times the mass of Pluto. We're trying to find the mass of Pluto. Now I've generated a value here as a factor multiplying mass of Pluto. I'll divide both sides by 1.137. And I find that the mass of Pluto roughly is 1.3 times 10 to the 22nd kilograms. And I've rounded off a little bit here. But we use this modified Kepler's third law when the two masses are comparable, and put in our values, and we come up with the sum of the masses. We take advantage of the sizes of the motion being a factor of 7.3 tells us that Pluto's mass is 7.3 times the mass of Charon, and then make a substitution, replace m sub c with m sub p divided by 7.3. So let's go a little further here. So we found that mass, 1.3 times 10 to the 22nd. Just to compare it to the mass of our moon is 7.3 times 10 to the 22nd. So our moon roughly is a little over 5 times the mass of Pluto. So doing a ratio here, 5.6 times. Now, what about the density? Density is mass divided by volume. We just found the mass of Pluto. To find the volume of Pluto, we have to use 4/3 pi r cubed. 4/3 pi r cubed. And the value of r was, of the radius of Pluto, was given in that paragraph at the start of the video here. So 1.188 times 10 to the 6 meters. I've converted from kilograms to meters. I want to come up with a density in terms of cubic meter. So 4/3 pi r cubed for a sphere. Pluto's nearly a sphere. And we get this value for the cubic meters, some perhaps slightly approximate, but our density, mass divided by volume. Again, you should pause and do your own calculation. I came up with 1,850 kilograms per cubic meter. Or if you want to go to grams per cubic centimeter, you just divide by 1,000 to shift units from kilograms per cubic meter to grams per cubic centimeter. So 1.85 grams per cubic centimeter. And I looked up the density of ice on the Earth that's not compressed. I get 0.92 grams per cubic centimeter. So why is this density higher? There could be some rock in Pluto that has higher density of 3 or 2 grams per cubic centimeter, but most likely it's the ice has been compressed under great pressure as you go interior to Pluto, and the density will go up as you reduce the volume. As the volume goes down, the density is going to go up. So as that ice is compacted, its density goes up, and we find about 1.85 grams per cubic centimeter. So ask your instructor if you have questions on this. If you'd like a list of more physics and astronomy, short lectures and example problems worked out, you can go to these websites. No registration. The websites are free. You'll find a description and a link to the YouTube video. If you like these YouTube videos, if you enjoy them, you could subscribe to my YouTube channel after you watch a video, and there's no charge for that. And I hope you keep on practicing your physics and astronomy problems.